Next act has actually sold out shows at the Adelaide Fringe, which I think is bloody impressive. But to do a solo show all about photons and to sell that out, that's impressive. So here to do a little bit of that show in the online flesh. Go, Rachel!
Oh, thanks, Phil. So I think I'm essentially leading off from where Chris ended up to do that little bit of quantized energy that we saw at the end of his book. So yes, very excited to be here. I am providing some light entertainment for you all with the illuminating, the brilliant, the bright, the not positively, the absolutely glowing photon. So right now, all of you at home are radiating at 24,000 gigahertz. And I can tell you are just absolutely radiating. Unfortunately for us panelists, we're only radiating to you at 2.4 gigahertz right now, having been uploaded into the digital stratosphere. Now, before I jump into photons, I just want to say, who here has grey hair? I know our wonderful host for this evening has some beautiful hair on him. Very nice, Phil. Now, I just want to say, congratulations. How fantastic. You are so lucky. Do you know why grey hair is really the best? Because from your scalps, you are growing glitter. And this is the most environmentally friendly glitter you can get. And that stuff's so expensive. And you're just producing it for free. Now, why is glitter so wonderful? It's because it's reflecting all those photons right back at you. See, my original very dark hair just absorbed all the photons. And honestly, what a waste. So selfish. All right, so now we'll get back to it. Now, what is a photon? Well, it's not something you're sleeping on at a friend's place. A photon is, well, what about this? All right, photon walks into a hotel. Receptionist says, oh, can we take your luggage up to the room for you? Photon says, no need, I'm traveling light. The silence on these shows makes this very hard. So yes, that's what it is. It is traveling light. Now there are three things to know about the photon. One, its name comes from the Greek word for light, which is also why we have photography. Two, nothing can travel faster than it. This is the speed of light we're talking about. Ooh, and then, what does a pirate and a photon have in common? They both travel at sea. And the third thing to know about the photon is that it is a quantized piece of the electromagnetic spectrum. Now, we had the word quantized just before with Chris. This is a packet of energy. In this case, it's a packet of light, of the electromagnetic spectrum. And this is quite simply everything. This is feeling warm. This is sending an email, receiving a phone call, microwaving leftovers, and just optically experiencing the world. So think of a rainbow. Yes. Ooh, I've got another one. Right. Where does a convicted rainbow go? To prism. But don't worry, it's just a light sentence. All right, now think of your rainbow. Now this is a spectrum. This is a spectrum of light, but it is a tiny, tiny, tiny little portion of a huge spectrum. There are so many colors that we can't see. And today I wanted to make them visible. So what I've done is I've collected images of the Milky Way from all these different parts of the spectrum. So the spectrum is broken up into segments. And before I show you these pictures of the Milky Way, we'll go through these segments. So number one, we have gamma rays. These are the photons that make the Hulk the Hulk. Then we have X-rays, which I was wanting to say Superman, but then I realized that his X-ray vision must mean that he absorbs X-rays, because if he was emitting X-rays, there'd be nothing to detect the X-rays. And then So something has to be emitting them, and then he's detecting them. And then I got very confused and realized it doesn't make sense, which is very unfortunate, but it is a comic book. I'll have to go and investigate further. All right, X-rays, and then we have UV, which we know about from sunburn, of course. And then we have the visible spectrum, the visible light, which of course we are most familiar with. And from there, which edge of the, one edge of the rainbow is smarter than the other. Which one is it? Well, it's the well-read side, of course. I'll work on that one. All right. So then we've got infrared, and this is warmth. This is sensation. When we're feeling the sun's warmth, we're feeling the infrared light, where the burning is from the UV. All right. Then we have microwaves. Bing. And what did one photon say to another? Nothing. It just waved. All right, and then our last segment of the electromagnetic spectrum is radio waves. And these are light. These are not sound waves. These are light waves. It's very important. You know, this is 4G, this is 5G, but definitely not BGs. Not at all. All right, so there you go. There are segments of the electromagnetic spectrum. And so now what I want to do is show you these beautiful images of the Milky Way from each of these segments. We've used our wonderful technology to turn these different photons into something we can actually see. So I'm going to share my screen now and go on a journey into the Milky Way. So here we are with our gamma rays. Then we have X-rays. I love this so much. Oh, I'm going to be out of time soon. All right. Then we have UV rays. There aren't great photos of the Milky Way in UV light. It's too much dust. It just absorbs everything. And then, of course, our optical view that we might be much more familiar with. And infrared. Love this. It's so dramatic. So what's next? We've got microwaves. Beautiful choice of purple, very bold, love it. And finally, we have our radio waves. And so there you have it. There's our trip through the Milky Way and the trip through all our photons. Thank you.
Stuff, Rachel. Okay, I now understand why it was a sellout show. That was so good. And just for the record, everybody, I want to say that the glitter on Rachel's top is not from my hair. that would be some seriously fast online, connection beyond the abilities of the NBN, I reckon. Unless they connect a 3D printer and somehow, yeah.
We'll make it happen.
Have we got any questions? Somebody says that is bad. I presume that's to my joke. Yeah. My brother-in-law should have been here. All right. A light-hearted presentation. Well done, Rachel.
Oh, thanks, everyone. That's lovely. And after not being able to perform at Sydney Fringe, it's nice to get this little moment to do it. So thank you.
Quantum teleport my hair. Maybe that's what happened.
Oh,
maybe we got somehow quantum entangled by not being in the Fringe. Both of us.
We'll stop there.
Are the different colours on the pictures different wavelengths within parts of the spectrum?
Yes, great. So the colours are not real colours. They're chosen by the research team to show different energies of the photons. So within each segment of the spectrum, you've got different energies in there as well of the photons. So each energy level has a different colour, and that's what gives you the full range of all the colours in there. So they are chosen
they must,
by the scientists. And so the infrared ones are usually always red. Because
choose a couple of representative colours and mix them up, right? Yeah.
Yes. So that's why I love the microwaves being purple.
That was from Sing Young, who actually was another scientist who was going to join my show in the Fringe. That got cancelled. So hello, Sing Young. And maybe we'll get you on stage in Sydney soon. It's got to happen. Here's another question from Aritra. Why is ultraviolet absorbed by the dust and not the other waves.
Oh, great. So this, if you remember Chris's book with those different electron levels, so the dust in the galaxy, those electrons, they have the same, that energy jump for them is the same as the energy a UV wave has. So that electron is going to jump to that next energy band when that UV light comes through, when it hits it. And so it doesn't get through the gas to us on the other side. So it's just that perfect energy amount for that electron.
So when we say dust, are we literally meaning little bits of dirt?
It's mostly hydrogen gas is that
Right.
dust.
Okay, so it's a pretty loose interpretation of dust. When I do the dusting at home, I'm not wiping hydrogen off the vases.
Because I think in astronomy, isn't everything a heavy metal past like helium, hydrogen, lithium, and then everything's a heavy metal?
Well, even lithium's metal, isn't it? So,
Very true. So I'll leave it to an astronomer to answer.
So
if
it were actual dust, as in a solid thing, then I think it would absorb everything.
Yes,
pretty much, wouldn't it?
I think it absorb a lot more.
Yeah. Actually, casting our minds back to, I think it was our International Women's Day earlier this year, we talked about Betelgeuse. Why has Betelgeuse got dimmer? And the answer may be that it seems to have a big cloud of dust in front of it.
Yeah.
But that might be literal dust, not astronomical hydrogen dust.
More planet-forming dust as opposed to
right.
hydrogen gas.
Yes. All right, Maxwell. If light waves are electromagnetic, are they attracted by magnetic fields?
Oh, well, this is where I start to confuse myself if I think too deeply about it. So
well,
yes.
I think the trick is that it's a very fast oscillating magnetic field. So
because it's electromagnetic because you've got a magnetic field this way and an electric field that way. And that's what the light is. And the reason that a magnetic field can induce an electric current is because of that relationship. So while I don't think you would be able to bend light with magnetic fields, yes, unfortunately, I don't know too much about that. But Phil, can I interrupt? There was a question above, which from Martin about what are the big blobs in the radio spectrum image?
Oh, yes.
I just wanted to say that a lot of those big blobs are the shells of supernova remnants, which I think is beautiful and very exciting. So the star is gone. We can't see the star anymore, but we can see that shell, that leftover shell in the radio spectrum.
So it's in the radio. What exactly is radiating the radio waves?
To be leftover. Again, dust. It's so encompassing.
Dust meaning hydrogen. So a gas. It's a kind of, is it like one of these shock waves? There's been a shock and this wave of this front of gas is traveling outwards.
And sometimes there's actually electrons too. You can have energized electrons that are still hanging around. As well, and just mixture of high energy particles or low energy particles that are just emitting that little bit of light still. Yeah.
I've got to say, I remember being shown, so hello to Martin de Sturck, one of my old colleagues from Sydney Uni. And I remember being shown by another colleague of ours, Dick Hunstead, some radio waves. And I thought, gee, that really looks like pasta sauce with balls of mozzarella in it. So they were the big blobs in my mind. But fortunately, Rachel is able to disabuse me of my Friday night hungry notion and move it right along. Okay, any more questions? 3 new messages.
Phil, that was the giant spaghetti monster that you're thinking about.
That's right. That's right. There goes the philosopher chipping in.
Oh, and thank you for everyone for jumping in and helping me with the light and magnetic fields. Really appreciate that. Thank you.
All right. You can't bend light with magnetic fields. Light is traveling disturbance in the electromagnetic field. Matter makes light bend. There you go. All right. The flying spaghetti monster is Tibor saying it's time. It's time to get philosophical. So big round of applause for Rachel.
Thanks, everyone.